So my summary is the following. As I said, I'm not sure that neither Yale nor Sean will agree with me, but at least I think that they presented almost two very different, and I don't know if extreme, but very different approaches. Yale start is a talk with, I don't care about what the industry really need, because the student will grow up and I don't care if they will study Java, C++, flat or whatever. Sean start is a talk about look at the statistics. We need people that will do Java, we need people that will do C++. Let's look, this is what is the target. So this is a very, very fundamental difference between the approaches, at least from what I view. You said, let's teach them the basics. The basics are the most important. The mathematics, the basics, and then they will take it whenever they like or what direction they like and so on. Shall look on on the education from a totally different, I don't know if totally, but from different perspective. We want the people to be productive. We want the people to go to industry. I want to hire them. I want to get the maximal productivity of them. And for that sense, productivity is how many line of code they will develop when I will hire them. So I think that this is a very, very fundamental difference between the two approaches. The other approach, the other main difference that I found is that although they almost use here almost the same terminology, so actually they almost mean the opposite. Yale cannot say, I don't care about x86 architecture because I can teach them the very principles from a simple ISA, that in this ISA I have other fundamental features that later on they will learn about the different architecture. Shaka said, from the software point of view, I want to run it once. Who cares about this hardware? Because a chain of two eventually will translate it to any kind of hardware. So who cares about the real hardware? So they almost claim the same thing. Who cares about the real hardware? But from a totally different point of view. One is from the point of view that from the basics that I teach them, they can actually leverage and understand all the rest of the architecture. And the other came from the point of view, the tool will do the work for them, so why to bother them to learn about all the structure, and about the architecture, and so and so and so? Because the tool will do the work for them. So maybe for the 10% of the people that will work on tools, they need to know all the basics. All the rest, I don't like to bother them with all the details, because it is not really important. They want to write once and run everything. So I think that these are part of the major differences between the two approaches. And first of all, I suggest that you comment on my summary, and then, if you can, please comment on each other presentation.
So it'll be a pleasure. So we need people who will program in C++. One of the best students I ever had ended up as an undergraduate. So the first thing I got to say is that we're talking about the freshman year. We're talking about the first course. We're not talking about giving the person a degree at the end of the freshman year. So if can we have two of these? If we have two of these, then it probably works, no? So if you put that, so does it pick it up now? It does, okay. With my voice, my voice tends to fill the room. I have been told that students tend to leave the room to make room for my voice. So you don't get the degree at the end of the freshman year. One of the best students I ever had broke my heart by taking a job when she graduated as a COBOL programmer because her husband expected her home at 5 o'clock to make his dinner every night, and the job that she ended up taking was close to where they lived, so she could do that. But she didn't know any COBOL, and so she graduated in December, and she started the 1st of January, and so she spent 2 weeks over the Christmas vacation teaching herself COBOL so she could then do the job. So what's the point? The point is that if you give them the fundamentals and you teach them the LC3 and you teach them the solid foundation, then they can pick up anything. They can pick it up in the classroom. I don't suggest that you never teach Java. I'd make Java a 1-unit course in the senior year, for example, maybe. But I wouldn't make it part of the foundation. Same thing with x86. I don't suggest that you don't know x86. I'm suggesting that the freshman year, if I teach the LC3, they can understand what's going on, and then later on they learn the x86. Or, in fact, what we're doing now in the curriculum, we've moved software all the way into the sophomore year. So the first course is what I told you about, and then the second course is the Motorola 6812, where they're programming it in an embedded system. And then they get the C++, Java, whatever, beginning of the sophomore year. We're talking about the freshman year and getting them started. So that's in response to what Avi said. I did have a lot of comments on what Sean said, and probably similarly he has a lot of comments with what I said. I'm not sure that I want to go through them all. There are a couple of things that I probably ought to do. One is this number 5% of the comment was that 5% will actually go on. I'm wondering if you're that 5%. So some people say, my research has been with embedded systems, that my research is really, branch prediction and out-of-order execution is only good for like 1% of the market. The other 99% of the market are systems that don't need any of this stuff. But what I do is for the only interesting 1% of the market, see? So what I'm wondering about the 5%, if there are two different courses, that is, I don't want to confuse a literacy course or a course for people that just want to know a little something from people who are going to make a difference. And make a difference in architecture, make a difference in tools, make a difference in software design. Microsoft developers who started with me in the course that I described come back, now they're 10 years out of school, some of them, and they say that the foundation you provided with the LC3 makes me grok. You understand the word grok? Yeah. Makes me grok how the computer works. That makes me a better developer at Microsoft, even though I'm never worrying about this low level. It's just that a model where they get it, say. Your comment that the program counter is not weird. The program counter, so in my book, I draw a picture of the program counter as a finger. See, the program counter, and by the way, Intel's the only company that's got it right. Program counters don't count programs. What they do is they keep track of where in the code you are. So I draw as a finger. It's like, you put the finger on the instruction, and now you do that, and on the next instruction you do that, etc. Program counter it's almost like it's a pointer variable for the code, as opposed to data. Some of the early machines got it wrong, by the way. They, one of the general purpose registers was a program counter. I think that probably got in the way of understanding. No, I'd rather not comment on everything, because then, and then he'll return the favor, and there'll be no time for the audience, which is a mistake, I think. So I think I'll stop there for now. Okay, so.
Okay. So on pretty much everything, I agree.
Good.
The one thing I do want to stress, though, is that with the program counter, seeing it as the scheduling process of the processor puts it in the same conceptual framework as the software, and it erases this artificial boundary between software and hardware. They're the same thing, and they should be thought about in the same way. And seeing it as the scheduling process, which is the same as a scheduling process in a software processor, brings everything together.
So there's no question. In fact, he's right. There's no question. Anything that can be done in software can be done in hardware, and vice versa. So artificial barriers, I'd certainly would prefer to to get rid of.
One small comment about the program counter, and then we move forward. One of the main differences when you look on the program counter specifically is the way that the hardware interprets the set of bits that it has in the memory. Because from the hardware point of view, memory is a collection of bits. And the only way to distinguish if this is a floating point or integer or instruction is by knowing if you are looking on the instruction through the instruction pointer, or you look on the instruction from some addressing of data. So usually, and this is much different than just looking on the sequence. So from your point of view, you say, okay, I have a chunk of work to be done. I couldn't care less if you are using a computer or if you are using drums, as long as you'll come back with the answer to me, and this is the sequence that I want to do it. And reality, maybe you're right, because sometimes you do it in this piece of hardware, on sometime else you'll do it with FPGA, and the third time you do it on a GPU. But from the computer architecture point of view, it makes a lot of difference when you execute something. If you want to understand how the hardware works, it makes a lot of difference if you access the same memory through the instruction pointer or program counter, or from some other mechanism.
Right. And when they go on into the more advanced courses that are architecture line, that's when those distinctions start happening.
I totally agree, and when they go on to the courses that follow the introductory, that's where those subtleties get brought out.
Before we move to the audience, I just want to have one clarification, one question for Yale on his part. I totally agree with your approach when you teach a brilliant computer engineers or computer science student. My question is, if you try to teach the same course for a student, you said that it should be for EE and so on. Do you think that you should use the same approach in terms of not using a computer added in emulation and so on, or maybe for just to bring the common material, not the advanced material, but only the common material, you want to use all this material that you can put on the web of animations and so on to make the average student to understand the background, and then you can spare the time in order to work with the 10% extreme good students about the advanced topics.
So these are not advanced topics. This is the freshman course. You're talking about engineering students?
Yeah.
The average engineering student?
Yeah.
So I start off with 400. I would say probably of the 400, maybe 350 passed the course. 50 either got a D or an F, dropped out. A large number of, so to get into the University of Texas, you have to be high up in your high school in Texas, which means you have to be able to memorize so you can barf back all the things that they've put into your brain. There's very little correlation, in my view, between being in the top 10% and actually knowing something.
Yeah.
Most of the kids take AP, Advanced Placement courses, which they go through this Java thing where they tell me they learn nothing. Many students come from rural areas where they've never seen a computer. So the prerequisites for what I've described in my 40 minutes or whatever The prerequisites are a brain that works and energy to use that brain. No computer science background whatsoever. And kids get A in the course, and I'm not an easy grader, with no background whatsoever. In fact, one of the big dangers in taking my course is if you had 3 years of advanced placement and you think you know it all, then you come to class and you don't pay attention, and before you know it, you're in over your head, and then you spend the rest of the semester scrambling. I don't consider, these are not the top 10% of the class. The average student performs. And in fact, one of the big things that, in fact, I might turn it on Sean a little bit. I wasn't going to do this, but I think I got to do this. This thing that you described, have you implemented it? Have you actually taught this yet?
So that's excellent.
So let me finish, and then, so the answer is yes? The answer is no.
The answer is
somewhere between yes and no.
The answer is we're in the middle of this.
Okay, good.
But we do know where it's heading.
Good. I want to encourage you to develop it, because frankly, sitting there, I was lost in several places. What I hope that you will do, and this is critical to learning, and it's so much at the heart of what I do, is when you teach this stuff, when you test, when you examine what they've learned, make them do something where they extend what you've taught them. Because I see too many courses in the university where they sort of, the cookbook model. They haven't really learned anything. They've just sort of soaked in stuff, and then they can impress their girlfriend at a cocktail party. But that's not what we're about. We're about taking what you've done and now taking it to the next level. And I'd be real interested to see whether you're able to do that.
Well, I actually want to ask you a question. I really like the LC3 concept of really simplifying things. And I'm not sure how much work this is going to be, but if I had my druthers, what I'd really like to do is apply that same concept to languages, so that this question of what do you teach first goes away. We're doing the same thing where we're distilling the essence of what needs to be learned into simple languages and following that. Yeah,
so that's one. So I had a comment. So when I was preparing this morning, and I stuck in that bullet about Scheme, and I don't program in Scheme, and but I've talked to one of the junior people that I hired. He's MIT product. And I've also talked to Abelson, who is, by the way, a scholar of the first rank. I wonder if Scheme isn't doing exactly that. That is, I wonder if Scheme isn't a bottom-up approach, except they've set the bottom. In fact, when you were talking, I almost, I almost interrupted you, actually. I said, I wonder if what you're doing is not really similar to Scheme. That is, you set this bottom, it's still bottom up, because Scheme is, because MIT's 6001 course is all about algorithms. And so they set this thing and then they go from there.
So I actually went to Berkeley and we used the Abelson assessment book and did Scheme, and I loved it. That was my favorite all-time class.
You're a Berkeley undergrad?
Yeah.
After I left, I guess, huh? Because you were that far.
That might actually be where you recognize me from. I took Clancy. I had Clancy for one of my classes. And the thing is that previous to current times, I would completely agree. The thing is, with the move to parallelism in needing to write one program that runs on all these different parallel architectures at the same time, Scheme unfortunately doesn't fit that bill. And I'd like to come up with some simple things that would have the same effect.
And I wish you luck doing that. The critical idea for me is, as you say, making it simple, and you like the LC3, is to, if you can do a model that has the parallelism in it also, where they can get it. And the test of getting it is to test them on taking it to the next level. And by the way, these are the average students, not the top 10%. Anybody can teach to the top 10%.
Yeah.
You can say Baba Black Sheep. Doesn't matter what you say. The top 10% will, get it by themselves.
So, by the way, MIT are going to drop Scheme.
I'm sorry?
as far as I know, MIT are going to drop schema. This is a different topic, but
I think it's a mistake if they do, but, you know.
I think you both agree that every student should understand at least the concept of memory and memory-to-memory operations. Now, there is then a question whether we should allow students not to understand, not to learn anything underneath that, and to just go ahead with memory-to-memory operations. At least those who will need to go to software and to learn many things about software. I got the impression that no, you don't.
We agree that memory is important.
But does everybody need to understand registers and?
So, in the introductory course, I think yes. But understand them in the context of some nexus of primitives, so that when they're in the software world, and the concepts that they're working with every day, it's a real simple place to go from those concepts down to the things that you get in hardware. But in the introductory, I think it's enough, and then go on in pick one of the tracks, or play around with them. But then in the application track, then you learn real languages, you learn real development processes, and then if you're going in the embedded applications, then you really have to know registers, and that introductory will have prepared you for it. And the reason why I brought up the C and C++ statistic is not because I think C and C++ are going to necessarily be the languages of the future, but it's because those programmers are very close to hardware. So they have, 1/3 of the people who are going into the programming track, they have to know about registers. So I think that motivates putting register visible stuff into the introductory course.
So yeah, so I don't know the answer whether or not it's enough to know memory. My big concern, which I think just permeates everything that I've said and everything I think, is the concept of disconnects. That is, the student has to have a model that makes sense, that he or she understands, that works. They may never, so they're never going to use the LC3 unless I get some company to manufacture LC3s and we replace ARM or something or other, I don't know. But my expectation is that they're never going to use the LC3 after the, freshman year, if you will. Can they have a model that makes sense if their foundation is memory to memory? I don't know. For me, the answer is no, but it may be yes. I think the scheme people would argue yes, that you can make that level, higher without losing anything. The problem with the scheme model, I didn't realize that Berkeley used the scheme model. At MIT, one of the problems with MIT is that anything that somebody refers to MIT has no relevance to the rest of the world. That is, the MIT student is very bright and very focused, and as I say, you can say Baba Black Sheep, the kid would still learn. So I'm not really good on taking what the MIT experience is and then applying it to the rest of us. For me, I need a model that they get. Even though they're not going to use it later on, it gives them a starting point, a foundation to then build. And I don't know whether memory to memory is enough. They certainly need to know memory to memory. But I think they need, like instruction pointers, which is what Intel calls the program counter,
Yeah, so I think I just want to bounce on this question. So, sorry, Albert Cohen from Minoya.
Is that on?
Yes. I have the impression that Sean's point has been slightly misunderstood here, because the point is not to say that, okay, you should not care about all these various architectural specificities, etc., if you want just to be an application programmer. The point he wants to make, my understanding, is that you cannot care, because there are just too many architectures around and you don't know where your program is going to run on. So what you have to care about, as you said, Yale, is that you have to understand what is the process of translating an algorithm, let's say, or a problem into some code that runs fast, assuming you want the code to run fast. So exactly as you said, you have to teach the data structure the new way. This makes sense for scalar processors very much, because you have to understand register, you understand what is local, what is remote, what is fast, when control takes time, etc. But for when parallelism becomes a very large part of the picture, what do you have to teach such that the students can forget about trying to think in terms of a particular machine? So they still want performance, and they still cannot rely on tools and ourselves as researchers to solve all the problems. We can't. It will take plenty of time. So they still, although the world is not as nice as we would like it to be, they still have to write the code in a way that will later be able to be adapted to run fast on most machines. And so we cannot tell them, this is a recipe, just do that, it will run fast. You have to tell them to understand how it goes through the different stages into running later fast. And this is unfortunately quite hard to get into just a freshman course. And so there may be a contradiction behind.
Right, and that's what the processor specification structure is all about, and that's what describing the scheduling process is all about, and the evolution of state. Because once they have those concepts and they've played with them and worked with them, they know that whatever hardware this program ends up on, they know that those are the things the tools are going to be using to get from here to there. They know that the things that they have to care about are the processor specification structure, the transform properties of plus or that have been tagged onto those structures, the dependencies, right? And they'll learn, they'll know a dependency in their sleep when they see one. And scheduling constraints. And if they know those, then they'll have an idea of what the tool has to work with, and they'll know how much parallelism they're exposing. They'll know how much, they'll know the ability of the tools to change the task size, which is key for performance. They'll know they'll know why they're providing a manipulator to the tool. They're implementing this thing that allows the tools to change the evolution of state in their code at runtime. They'll know why they're doing all of these things.
Just be a little more cautious here and say that we should aim for a course to make them know, but it's not clear that it's easy to adapt the course that way, but it should be the direction. Eventually they should know.
So let me try. In the senior course, what I have them do is implement in Verilog a processor, and it's a subset of the x86. And they do the data path and the state machine. They start with a clean sheet of paper, data path, state machine. They do a bus. Dumb controller, or the sophisticated controller, etc., cache, memory. And I said they do it in Verilog. What I didn't tell you was they do it in structural Verilog. They don't do it in behavioral Verilog, see? And of course they bitch and moan, but that's okay. Then they graduate and they get a job. Now most designers operate in behavioral Verilog. They don't operate in structural Verilog. You got tools that'll do that for them. But if they don't know how the structural Verilog works, in fact, so I have reached the level of my incompetence where I'm on design reviews for some of these companies, and I see this speed path. And the speed path was done by a young designer who didn't know the structural, and he just does it at the behavioral, and so the tools create this sequence of propagation delays that no serious designer would do. It's not that when they get out, they're not going to use the tools and operate at behavioral level. It's that if they operate at behavioral level and they don't know what's going on at structural level, then they're screwed. So let's go back to the LC3. Maybe what you're asking for, I don't know, is we start with LC3 and then at some point it's LC4, which involves a couple of primitives that allows two LC3s to talk to each other. So my factorial example, for example, I'd add a construct that would fork there's no forking processes in my LC3, that would allow this other thing to work, and now you've got the dependency, right, and the synchronization. Do 5 factorial, chug, 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 and now wait until this comes back with the 5 factorial. But again, we start with something that they can get.
Or just a queue that's not implemented in terms of threads, just a hardware queue that does its own thing. That would solve the problem.
I have a question for you about your part. You claim that you want to have one program that fits all the different architectures. Actually, I wish that we could do it. In practice, if you just take two architectures which are different in their cache structures, or if they are different in the speed of the synchronization, or if they are working in out of order or in order, you may need to use different algorithms. So it is not just a matter that the implementation is different, but you may need to build a different algorithm. Just for example, if you build something for GPU that use a lot of parallelism, you need to create hundreds of threads, otherwise it won't work. But if you want to run the same program on general purpose, you need to make sure that you don't have more than a handful number of threads, because otherwise it won't work. So how you can separate the understanding of the architecture from one even algorithm fits all?
So those are really good points. And what you'll notice that what was going on is not that the algorithm is necessarily different, but that the scheduling process that you implemented as part of the application is different. And once the concept of scheduling process, crystallizes, then it's painfully clear when a scheduling process is being done as part of the application. And if instead that program was written such that it's exposing the constraints on scheduling, then there would be as much parallelism as you can possibly specify, by hand doing the most, crazy things. That gets exposed to the tools, and then the tools get to choose, okay, am I going to do small little ones for the GPU, or am I going to do this big one for multi-core? And there's absolutely, that's part of the work that we're doing right now, and there are a lot of results in the parallelism world that are moving in that direction. CNC from Intel is one step towards that direction. Some of the things coming out of Stanford, and that's the place where things are going, and those are the things that are having the most success. And that's the only thing that will allow the future to have the same economic model as the past. So there's just enormous pressure to get to one program, multiple hardware.
When a young person first learns programming, in the past they always first learned sequential programming and then possibly later on parallel programming. From now on, should they learn parallel programming from the very first beginning or not?
So in the slides with the two iterations, the first iteration was sequential in the application track, in the introductory course. So the first thing they would be doing would be sequential programming. And it would be in terms of memory-to-memory operations. So in their language, they have the model that each of the statements in the program, they see how the language is scheduling all the intermediate results in there. They see how the local state to the software processor that's created from each function, how its state is evolving according to that language scheduling process. And the fact of knowing about software processor being created and the fact of knowing about the scheduling process, and they would also see dependencies in there, those are the three keys to parallel programming. So without even knowing it, they've already learned about it. And then in the second portion, introduce patterns, parallel patterns. Once they've had the hardware and the primitives have been mapped onto the hardware and they have a better understanding of the communication that is implied by each of the things that they see in their program. Program, I access this variable, I write it to it, and then in the program I read it. Well, they're going to have seen that it means that this big long communication through the cache hierarchy. So they're going to know how that leads to parallelism when that one piece of code is duplicated in two software processors on two different physical processors. So the parallelism is in there at the start, even though they don't really know it yet.
So I'm a big fan of starting simple and moving from simple, concrete to more and more complicated as you move along. So I think the key notion is to not tell them that parallel programming is hard. It's just the next step. So the first thing they would write would be a sequential program. In my course, by the way, that first sequential program is written in machine language, zeros and ones, and they only do one machine language program because it really is tiring. And then we move to assembly language. But I have fooled with the notion of, as I said a few minutes ago, of adding parallel constructs to the LC3. If I could do that, if I can, so far I have not figured out how to do that in a clean, neat way to get them to be able to not see a major hiccup. If I figure that out, then I would say, sure, first couple of programs are sequential, and then we give them things to do. And so my multiply example, for example, compute 10 factorial, and you have to do it in less than 7 multiply times or something or other. So I constrain the problem, so that a sequential solution doesn't satisfy the constraints of the problem. But to be able to do that, I need to have constructs in the LC3 to handle that. So I think the same thing goes if I didn't do LC3. If I was teaching a high-level language, I think that all the same things hold. That is, the first couple of programs are sequential, but does the high-level language have the parallel constructs in it in a seamless way that I can then give them the third program to do, for example, and constrain the problem so that they have to come out with a parallel algorithm. And never tell them that it's hard, right?
You still have one opcode free in your instruction set. So
I'm sorry? I still have one opcode, yeah, right. Yeah, so what I might do is make that be like Intel did with their first. So you know that all Intel opcodes are either 1 byte or 2 byte. In fact, the VAX did that also. See that once you run out, you say, okay, pointer to this page or something or other, and then I have another. So.
Okay, I think we are agreeing too much here. So I've tried to play the devil's advocate and try to raise some controversy. And I hope Sean will forgive me. So basically you have been defending the idea that computer architecture has to be there in the freshman course from the beginning, even without stating it explicitly, because performance matters.
Computer organization, I would say, rather than architecture. But yeah.
So this was like not even stated, and in this community I understand that. But maybe we are mistaken. Maybe because of the way let's say, I hate to say the market or the need for programmers is driving us, and also because of the tools. Most programmers, so if you just want to count how many students are getting out of school, they won't really care about performance because they will use libraries that will be fast enough. They will just assemble some components to do things. So I don't really endorse that statement, but it could happen. So in this case, shouldn't we have like freshman courses that stop much earlier in terms of how much understanding of the machine they need to have? I completely understand the Yale statement that they have to be completely demystified in terms of how the machine does the work. At least it should not be mysterious, but how detailed should it be? So if you want to be simpler, could we remove all these registers? Apparently it may be possible. If performance does not matter, we can cut like 4/5 of Sean's proposal. Basically, they need to understand some primitive components like dependencies, invariants, processors, etc. And that's it. And then they move to another story. So maybe I'm just going to raise that.
So I made my comment about the developers at Microsoft. They don't work in architecture at all, and yet they claim they are much better developers at Microsoft because of my freshman course. If you can come up with a model that they can really, that gives them a foundation they can build on, then I'll listen. But that's what it's all about, I think, is that there can't be holes, there can't be disconnects in their understanding. They have to feel that they get it. And then they keep moving up, you know. And if you eliminate it and they never get it, then I think it's problematic. Now, I frankly didn't understand a fair amount of what Sean put on the board, but if at the end of the day what he put on the board provides a foundation that they can then build on, then I'm okay with it.
I think that the question was a little bit different. The question was, suppose that performance doesn't matter. If performance doesn't matter, so we don't need to teach them almost anything. And by the way, suppose that mathematics doesn't matter, suppose that all the other courses doesn't matter, so let's teach them Java and let them lose and go to...
So I get seniors, I get kids coming out of high school that have 3 years of Java and they're completely clueless. What they've been learning is patterns, and then they get a problem and they try to find the pattern that maps to the problem that they've been given. That's not learning, that's not understanding.
My point is more, let's start from your course and remove stuff, but not removing the continuum from the switch to the operating system and C. Can we remove some stuff if performance doesn't matter? Oh, yeah, sorry. Is it possible to remove some stuff from your course if we just forget about performance and just keep on this main goal of making sure everything makes sense from the bottom up?
Can we assume that performance doesn't matter?
I don't think it's about performance. So for example, let me give you an example. When I first developed this at Michigan, and Trevor taught the course, and we included in that freshman course all the introduction to C as well, one semester at Michigan, which they do at Illinois now, by the way. Sanjay teaches at Illinois, and there are half a dozen faculty in Illinois that have taught that course, and in one semester they do the whole thing. So at Michigan we did that, and I was positive that I did it step by step and there were no disconnects. Trevor then taught the course and said, Yale, you're wrong. There's a major disconnect. It turns out when I got to Texas, we introduced C in that first course, but we didn't do the full-blown C. That's the next semester. So I had more time in the one course, so I was able to do it a little more carefully. And I'm up at the blackboard and I go, wow, Trevor was right. It's 5 years later I discovered this. What I didn't have in the course, it's in the book now because I immediately put it in, was finite state control. And I didn't see that was absolutely a necessary point between the data path and the logic and how a computer works, because the program counter sequencing through, that's finite state control, and I didn't have that in the course, see? So Trevor picked up on it when he taught the course as a major disconnect. I'm all about having no disconnects, right? And so it's not about performance, it's about building and building and continue to build.
In mapping that into the primitives I'm proposing, the finite state control would be the scheduling process. and to address what Albert was proposing, which is that who cares about parallelism, because you just keep writing your sequential programs because People don't care about performance in the future. There will be people who they just want productivity of programmers, and if you're 100 times slower, who cares? Code works. And the way I address that is with saying the purpose of the course is to take the benefit to each student, sum it, and maximize that. And if you look at where the students are going, I don't care about the people in industry benefiting them. I care about the students who are entering industry and benefiting those students. And they will benefit from fitting into the way economics work. And economics is a Darwinian process. So if you've got, you might have way out at the edges some company that really can get away with, only developer productivity, and you don't care at all what kind of performance comes out of it. But if there's any kind of competition, the sweet spot, the Gaussian, most of the places where those students can end up are going to be places where they've got competition, and if one of them worries too little about performance, one of the other ones can eat their lunch because they can provide better features, cooler graphics, better whatever, no matter what field it is. And that argument, performance doesn't matter anymore, has been used for the past 20 years. Everybody said, word processor is fast enough. We don't need any more, any processors that go any faster because all the applications we need, they all work. And yet, processors, people have continued to find cool features that people want that use that extra performance. So it's a good bet based on the past that the future performance will still matter. So performance means that when you write that one piece of code, you do want it to run well on all the different hardware platforms. So if you're going to be in that paradigm where one software, all the platforms, then teaching the students the foundation where they have a model of what the tools are going to do so that they can write code, like Yale was saying. The Verilog, the student understood the structural, so they knew what the tool was going to do. So when they wrote the code, their employer liked them, right? That benefited the student. Right? At Microsoft, the other example he gave of, because the student understood the foundations when they wrote their code ran better and their employer liked them better. So even though teaching to the tools is teaching them a model, and the whole fundamental thing behind that model is performance, it still benefits that student to know about that performance.
I agree. So I failed, basically. I need to find another controversial statement. So now let's take the exact opposite angle and consider that everybody is listening to Microsoft and Mark Sneer, etc., that people should be taught in parallel from the first year, from the first course, which I disagree with, and you as well. So, and then people will stop using your book, basically.
I'm sorry?
Then people will stop using your book because they won't find what they want. So what is worse? That they stop using your book and mess up completely with one generation of students, or that you very quickly figure out a nice way to add something for those guys? I don't know.
If my book ceases to add value, they should stop using my book.
Although I think that the hardware course, I think he's nailed it, and that'll be used for that track.
More questions? Okay. So thank you.